How do I make this?
We'll have to go. I'll go to the toilet.
Can you enable sharing my screen?
Yeah,
We can make you co-host even.
doesn't have to be Lucas's computer.
Oh, how come you're...
No, it has to be Lucas's computer, right?
How come he's still host?
Made him co-host.
Alright, yeah. Should be able to do everything we can do now.
Can you see that?
Yep.
Okay, so basically we're trying to write a program to find vertex transitive graphs. So have you gone over like the one ball construction?
Yes.
Okay, so this is attempting to implement that one ball construction. So far it's working sort of like trying to extend one vertex at a time. So what we're doing is we're picking the vertex that has the largest degree in this graph, and then we see if we can find a partial isomorphism. So it's isomorphic to part of whatever one ball we're looking at so far, and if we can find that, we can then try to extend the graph along. So it either keeps doing that until we tell it to stop, it finds a vertex transitive graph, or it finds that it can't extend it any further.
Oh, structure code. Oh, it's fine.
This is the code that we have so far. Have you done any coding before?
Yeah, I know Python, which I'm pretty sure this is, right?
Yeah, this is Python. I'm not saying it's the best Python in existence. No. Okay. So when you start off with a graph that you're starting with, and it's going to run this function recursively on that graph. So because we don't have an infinite amount of time or memory, you have to tell it when to stop, basically. So that's what the number of steps is. And you can also tell it to remove all the graphs that it finds that are the same graph at the end in order to reduce the size of your output. And you can also tell it to try and find finite vertex transitive graphs. So you start off by creating the cone or suspension of your starting graph, and the suspension vertex, the vertex you added when you create the suspension, that's going to be vertex 0 in the graph labeling. So that's going to be the only vertex in the graph currently that we know is the one ball there is isomorphic to a suspension, basically. So then you add so then you add each graph vertex to this list that we're going to need later, basically, and you create a copy of that graph. Now, down here, what you basically need to do, so each vertex in your graph that you're working with, it's probably not going to be isomorphic to the one ball that we want it to be isomorphic to, but it could be isomorphic to a subgraph of that one ball that we want it to be isomorphic to. And if you find that, you can then figure out how to extend the graph from that vertex to make it connect up nicely. It'll make it isomorphic through that graph that you want. So this function, not this line here, this function just finds every possible subgraph of the one ball we want everything to be isomorphic to. And then you need to also try and remove edges from it, basically just in case you need to, if is isomorphic, it has the right number of vertices connected to it, but it just is missing a few edges that you need to connect to. And right, so then this other stuff is just some variables you set to determine how the function is running, and you have a progress bar here, which is nice because sometimes it can take a long time to actually output, so the progress bar lets you know that it's actually running.
Right. Yeah.
So then you're going to run the recursive check function, which is no, not that one. We'll get to that one later. Right. So here, this is the function that you just keep on running recursively to try and find a vertex transitive graph. So you input the current graph, the graph you want every one ball to be isomorphic to, the degree of whatever your one ball center vertex is. The good vertices, those are the vertices that are currently the one ball at them is isomorphic to the suspension graph in the original. There's a lot of graphs to keep track of, it gets kind of confusing. So the can't connect, that's a set of vertices that you're not able to add any more connections to. The current step is whatever is how many times this function has been run recursively, and the number of steps is when you want to terminate. So then, now in here there is a whole load of stuff that you need to have it work nicely, but then the idea is that if you've reached the maximum number of steps that you've set before, then if you found the graph there and it's reached the number of steps, then you haven't ruled out that the graph can be extended to be vertex transitive. So either it will terminate at a future point because it can't extend, or it could extend to an infinite vertex transitive graph. So because you haven't ruled it out yet, you output that graph. Otherwise, you get a list of vertices that you can connect, or the list of vertices that you want to extend in your current graph. Then you sort them by their degree in descending order. Then you pick the vertex with the highest degree. You find the one ball there. And then here you're setting the vertex coloring so that the one ball, center of the one ball will map to the suspension vertex in your original graph. So you're only looking for partial isomorphisms that map the center of the one ball to the suspension vertex in your graph. Then if it has the same degree as that suspension vertex and it is an isomorphic, then you need to check if you can connect any edges to make it isomorphic. So that's what this part does here. Yeah. It's a fairly long bit of code there, but basically that's just trying to find if there any way you can connect different edges to make it isomorphic to the one ball. If you can, then it does that, and that's all good. If you can't do it, then you can't connect up this graph. You can't connect up this graph and make it vertex transitive, so that's the end of that graph. So then if they are isomorphic, then, oh, okay, yeah, so kind of difficult to keep track of this. So this one is checking if the degree of the percentage of that one ball is the correct degree, then they're not isomorphic. You try to connect up the edges. But then if they are isomorphic, then you just add, then that's a good vertex. So you add it to your set of vertices that work so far. And then, right, so if every okay, so then you add it to the set of vertices that are good so far. What's kind of bad terminology, but it's stuck now. So then, if the number of vertices that the one balls are isomorphic to your center graph, if that's the number of vertices in your graph, then you just check if the graph is vertex transitive. If it is, then you found a finite vertex transitive graph. Otherwise, you haven't. And otherwise, the graph can't be vertex transitive. And then down here, this is where you try to extend the graph. So we'll get back to the finite connection part later, but this way you basically just go through each possible subgraph that it could be isomorphic to. You check if they're isomorphic. If they are, then you extend that isomorphism by adding new vertices to your graph. Oh, so each possible subgraph. So this is a partial isomorphism. So like it could be, I don't know, you can't really see that, can you? But it could be like isomorphic to 3 of the 6 vertices, and that's suspension graphs. And then if you have that partial isomorphism, you can then figure out how to extend that graph. So that's what this part of the code does. And it checks that it extends it correctly. And then if it does extend it correctly, it then copies that new graph to a list. And it keeps on doing this for each possible way to extend the graph and each possible vertex. So then, if it has found any graphs that work basically, if it's found any graphs that still extend in this part, then it calls the same function on every single graph in that it's found that it can extend, and it just runs the function again until it reaches the number of steps that you've told it to stop at. And if by the end of that it's found any graphs that it has ruled out as being not vertex transitive, then this entire function will return, yes, it's found vertex transitive, or return true and say it's found vertex transitive, otherwise it will return false. So then, all the way back up here. Yeah. So here, this is the part that we skipped over before, where it tries to find a finite vertex, a finite way to extend the graph. So this one essentially does the same thing as the previous function, but rather than adding new vertices, it tries to connect it up to existing vertices in the graph. So it's just trying to find every different combination of vertices you could try, or permutation of vertices that you could try to connect it up as. And then, yeah, so then just runs the same thing where it tries to extend the partial isomorphism, but rather than adding new vertices, it tries to connect it to the existing graph.
Sorry.
That's all right. And then if it does find a way to extend it, then it adds it to the list of new graphs to run the recursive function on. And yeah, that's basically it. Now, that's probably like a whole load of information overload. So yeah, and looking at the code doesn't really help that much, and it probably would be easy to just look at it like a list of steps rather than all the details.
Yeah, probably, but it doesn't matter.
So yeah, so that's how the current program that we have working there. And probably the part that's a bit more interesting is actually seeing the program run. So do you have any particular graphs you want to run it on?
It's like to the
Cool.
yeah.
Alright, two disjoint squares.
Two disjoint squares.
Two disjoint squares, is that?
Yeah.
All right.
Okay, yeah.
Okay, so now we need to figure out the adjacency matrix of it. It's easy to draw it up, right?
Yeah, so we'll. There's input by writing in an adjacency matrix. Are you familiar with what an adjacency matrix is?
No, I don't think so.
Oh, it's just the entries tell you which one. Like 1 if they've got an edge on them, 0 if they don't.
Oh, okay.
Oh.
That's right.
Yeah.
So we have two squares. And what? Where do we start numbering? 1?
Yeah, 1.
1, 2, 3, 4, 5, 6,
I would have thought the matrices would
7, 8. So
groups would come up.
Row
1, 1, 0, 0, 0, 0.
Yeah.
2 goes into 1 and 3. 3 is adjacent to 2 and 4. And then we get another copy of this down here. So, yeah, there's 4. You need a 4 by 4. 4 is adjacent to 1 and 3. And then we say into the copy.
Okay, assuming I didn't.
Is that correct?
Probably they just cooked this. You just get a string of 1s and 0s. Yeah, that's it. Assuming I didn't make any mistakes when typing it. We'll start off with 2 steps. We should be a bit safe here.
Right, so you're going to go through 2 steps.
Yeah, I don't know how long it would actually take. So, okay, so here we're running the program by telling it the line representing the graph that we just wrote, and we're running it for just 2 steps here because I don't know how long it's actually going to take to run.
Well, the answer is going to be the octahedra joined in vertices, isn't it? So,
Fair enough, yeah.
And then we just draw another octahedron here. Is that how it looks?
It looks to be a cube. It also just be a cube.
Cube.
Oh wait, no. Yeah, okay, never mind.
Yeah, cubes have vertices of cubes have 3 nodals.
Yeah. Right.
If a single square, the answer is an octahedron. 2 squares. I suspect it's
You want to try running it with a finite connection? Or should we just let it go infinitely for now?
it's just going to go infinitely.
Right, so yeah, we're telling it the file that we just created and we're running it for 2 steps. The squares.h, that's the output file. The -m is telling it that it's in a adjacency matrix format. And the -u is telling it to output the unique mass found, not just every single graph it finds. Here we go. It worked.
Oh.
I hope. Or it didn't. I didn't actually tell it what to run. Nope. Okay. It ran with 2 steps. That's good. Always nice to know that your work works. Okay, so that's what it found just by running all 2 steps. You want to try running it for more steps or visualize it?
Well, can you visualize that one?
Can you visualize it? Yeah.
Right. So this other program is just running it through a program called DOT, which is designed to visualize graphs. So this program just is written to run that conversion automatically from our output. So those, they don't look very nice. But actually you can kind of see, yeah, you can see that there's a tetrahedron.
No, it's a square pyramid.
A square pyramid, yeah. So you can see those square pyramids forming there. So this is probably because we're trying to, it's just creating a bunch of new vertices and wants to extend rather than trying to.
So 0 is where it starts, is it?
Yeah, 0 is where it starts.
And it's done nothing with 1, 2, 3, 4, but then it's added things to 5.
Well, I think 5, 6, 7, 8 is the other square it started with.
Yeah.
So 0 is the suspension vertex. And I think on the other side of 5, 6, 7, 8, it added 9.
Yeah.
Then same thing down with 8 and there. It's actually visualized pretty well. It's sometimes quite surprising when the graphs visualize nicely.
Yeah. 5, 6, 7, 8.
You want to run it on an awful visualization engine?
What other visualization?
One that just makes a circle.
Circle. No.
Did that run well? Well, it's meant to run awfully.
That's the same graph with a different visualization.
Yeah, different visualization.
Oh, wait, that's true.
So yeah, you can see here there's the square. That's the vertex out in the suspension, and there's another square somewhere down there. 5, 6, 7, 8. And 14's just hanging on there for some reason.
The 14 is adjacent to 6, isn't it? 9 or no 7?
Yeah.
7 and 9.
And 5.
Oh, yeah. So that's yeah.
I think
5 and 6. 5 is adjacent. 9. 9 is adjacent to 5. 7, 14. And 8. Oh yeah. Yeah.
Yeah.
So those vertices 0, 5, 6, 7, 8. Nine. No, it's not 5, 6, 7, 8, and 9 are an octahedron, is it? Because there's 14 is in there as well.
I think 14 might have been added at some other when it was extending some other vertex, and it just hasn't got around to fixing the other vertices.
So, is there an example of like part of an infinite one?
Sorry, what was that?
Is there an example of like outputting part of an infinite one?
I still didn't quite capture it. You're talking about infinite?
Like would it? Can you show an example of the output being part of an infinite one?
Oh, part of an infinite one. Yeah.
Uh,
Well, this could be part of an infinite one, but
Oh, is it? Oh, okay. My bad.
that's there is that free path, I think.
there's what?
Like the free path that produces the nice.
Yeah. Yeah. So we'll put in the 3 dot example.
Okay.
Oh. 2 dot. Oh, it's a tree. Is it a tree?
Yeah, I think 3 additional points.
Um, 5, 7. So,
No, 3 dots doesn't work. 4 dots.
yeah.
So when 4 vertices, or do we want it? We want one that doesn't work, or do you want one that's infinite first?
We can do both.
I don't know if I have the let's see.
So 0, 1, 0, 0. So 1's adjacent to 2, 2 is adjacent to 1 and 3.
2 and 4.
3 is adjacent to 2 and 4. And 4 is adjacent to 3. Yeah.
Okay.
And once you start to get a reasonably large number of vertices, it's very hard to visualize,
Yeah.
Oh,
which is
Returning to the program.
that's right. Why we're using the computer, because we can't picture it.
Although we're running into a problem where once you have a large number of vertices, it takes forever for the computer to actually run.
Yeah.
Yeah.
So 4, nice. Okay. All right, I did try and connect to the finally. Okay, so got one of there we go. We can make that a bit bigger.
So it's output several graphs. There's
Yeah,
several
it's
answers.
found several graphs. And, eventually you find one where it produces a nice visualization.
Mhm.
So in this one, it started with the 4 path, or is that one's called a 4 path of like 4
Yeah, or 4 vertices and
4 vertices and a line.
3 edges. Yeah.
So it started off with vertices 1, 2, 3, and 4. Then vertex 0 is the suspension vertex that it added. And then in this output, it went nicely along, so it added vertex 5. Vector vertex 3 probably, yeah. So vertex 3 was almost isomorphic to what you started with, but it just needed an extra vertex, so that's where vertex 5 came from. And then it kept adding 6, 7, 8, 9, 10, and 11. So if you imagine this same, I guess, alternating trines, how would you describe that?
Well, it's a band, really, isn't it? Just a band.
Yeah. So if you imagine this band just extending infinitely along,
Yeah.
then you would end up with an infinite vertex transitive graph. Then also, back at the start, it bound, I believe that's a finite.
Finite one.
Yeah. So you can also find finite vertex transitive graphs that have what we started with, the suspension of that as its one ball. So yeah, 1, 2, 3, and 4 is the original path. Then you get vertex 0 and yeah, 5, 6, 7, 8, and that should finish. Oh, we could actually just look at the output and see if it's finite. So, all path have a finite extension.
It does. We can just wrap the band up.
Right. Well, the program isn't finding it.
It's not finding finite ones. Yeah.
That's a problem for future markers. So,
I was hitting up for a bit now. That room's out of bounds. That room's out of bounds. Yeah. Alright, yeah.
See ya.
so now we can look at 1, that doesn't extend. So here we're looking at just 3 vertices and 2 lines. And this is one that doesn't extend to the extrinsic graph. Oh, enough steps. Well, maybe it does with broken math. Graph. No, 0 steps in the show. Right. I think I mislabeled one of the files.
Right. That's a
That's the
toolpath. Yeah, we want the 3.
Okay. Whew. That is the toolpath. Okay, we can make it pretty hard. So vertex 1 connects to vertex 2. Okay, I hope this one actually breaks.
Wow.
Okay, so yes, there we go. Whew. Good news. Yes. So for the free path, we probably showed that as an example.
Yes, I've already worked that one out. Yep.
Yeah, so the free path, you know that it doesn't extend to a vertex transitive graph, and the program confirms that, which is nice. And
Path 1 step longer, we found the solution. What about 5?
that done. Yeah, it's the H1 extension, right? Or the 5 paths. Let's have the 5 slides.
Let's try 5 vertices and 4 edges.
Right.
Did you think about that one?
Yeah, we did. And the pentagon as well. I don't think the pentagon.
1 0 1 0 0. Okay, 0 1 0 1 0 0 0 1 0 1.
Five steps might have been a bit much for it.
Oh, good.
want to try running it on a smaller numbers.
Well, let's do it a little bit longer. What did you find for the pentagon?
I tried. I'm pretty sure it doesn't work because if you have like a another pentagon, the degree goes to like it becomes 6. You have 2, and if you have 1, it's uh, like you can't add you can't tessellate it because the degree goes to like 6, unlike the other ones like a heptagon or something. And if you do the thing with octahedron, there's too little. The degree is like only 4. It's not enough. So I'm not really sure why I think it works.
So you didn't find a graph.
Nah, but maybe there is.
Computer's taking a long time with this one.
Yeah. I think we should run it on a smaller numbers then.
You think it's getting closer to the end?
It's always getting closer to the end. I took algorithms last semester. I can actually talk about the complexity of it now.
Oh, good.
It's not a very nice time complexity.
Did you learn how to make it, how to improve it?
Not actually fix it. Yeah.
Who was teaching algorithms?
No.
Oh.
I think we should stop it.
What do you think? Should we stop it?
Yeah, sure.
Yeah.
Give up too easily.
You won't do it. We'll try running it at 0 steps. Perfect timing. Okay, that's reasonable. I think we should stop it at 3.
All right. So
There's also another problem. It just when you run it again and on the same output file, it just appends the new output to the end of that. So if you use the same output file over and over again, you don't get it with the graphs from one run of the program.
Sorry?
So when you run it on the same output file, on an output file that already exists, it just puts the new graphs at the end of that output file.
Mm-hmm.
So if you like run it on the same output file but different runs of the program, it'll just output all the graphs to the end of that. So if you run a visualization on it, you'll end up with graphs that didn't come from the output of that specific run.
Right. All right. What do we get?
Well, we get a really long yes, for 19 is probably why it took so long to visualize. Oh. Okay, so we're just going to look at the first 10. So, yeah. Messy. Okay, that looks a bit nicer.
Right.
There you go. Let's go 1, 2, 3, 4, and 5. That's the original 5 path.
4 has 5 neighbours, and then
Yeah, looks like it extended off 4. And
3
3.
has 5 neighbours. That's 4. That's 3.
Well, we didn't only run it for 3 steps, so except for 4, 3, then run
So the reason this is, what was that? Well, it was
1 and found. Yeah, that looks a bit nicer.
yeah.
0, 8. Yeah, okay, so here it extended off 4 and then 6 and then 8, and those were the 3 steps it took before terminating.
Yeah. So 0 has 5 neighbours. 4 has 5 neighbours, and it's path 3057. 6 has 5 neighbours, and path 547.
Maybe a battery.
8, 9.
Yes.
So is this going to continue, do you think? But the stones look like there's could be a solution, doesn't it?
There's like three,
Yeah.
three, 5, 7, 9, 11, 5, 7.
Okay. So another thing that is, I think the 5 cycle, which is just a pentagon running on that. Yeah, okay. Okay, so running it on the pentagon. Okay, so the pentagon is a pretty interesting one. Because it outputs two graphs. to visualize them. Okay. So this looks really messy, but I'm pretty sure that's the icosahedron graph. So do you know what an icosahedron is?
Yeah.
So that's the graph representing it, and that's what you get when you output from the life cycle.
This is another example, is it?
Yeah, it's the life cycle, and it's the really annoying one.
Oh, it's like a hexagonal prism with like the sides. I don't know.
Really annoying one because it's the one that can't extend to an infinite graph.
It doesn't complete your vertex transit graph at all.
Yeah, it does. It only does it to a finite one. So it's the annoying edge case you have to check for.
How do you know it extends?
I'd say,
How do you know it extends?
because that's the output. So this one is the output running it on the 5 cycle. And it says that it's a vertex transit graph. It's actually a finite one.
Right, okay. Oh, I see. I'm just looking at 9. So it has neighbors 7, 11, 7, 6, 8, and 10. Don't
Try a different visualization. This one's
I? Yeah, it's really hard to see. Oh, you started with the pentagon here.
Yeah.
Oh, right. Okay.
Now you're changing your to the 5 cycle before.
Did I?
Yeah.
Oh well, it's also a pentagon.
4. It's a bit better, I suppose.
Right. Yes, this should be an icosahedron.
Yeah.
So 12 vertices. How many edges?
Oh, it's that.
12 vertices, 20 faces.
Yeah. So isn't there a formula for it?
Yeah.
Wait a try.
The Euler formula.
Yeah, you have to specify which one. So how many vertices? 12 vertices.
12 vertices,
And 20 faces.
20 faces.
Means that equals 12 plus 20 plus 2. That doesn't make sense.
Icosahedron.
So what? There's 12 vertices.
Yeah.
Icosahedron.
Each one has 5 neighbors.
Yeah.
So that's 60. But then you're counting you're counting edges. So each vertex has it's 30 edges.
Right. 30 edges.
Each vertex has 5 edges adjacent to them, but you count each, so that's 60. You count each one twice, so it's 30 edges.
Right. So then 12 vertices minus 30 gives you minus 22. Right.
Well, 12 plus 32 minus 30 equals 2.
Yeah. Yeah, there are 20 faces. It's an icosahedron.
Yeah, yeah. Yeah, 12 plus 20 minus 30 is 2.
We can do arithmetic. Yeah, when you have your pentagon, it can only extend to the orthosahedron. No infinite.
That's right.
Thanks for that math.
Well, we knew that. The triangle, the square, and the pentagon, they only have finite extensions.
Yeah.
The hexagon goes to the plane, and then the higher polygons with higher order, they extend to hyperbolic planes.
We have the 6 thingy in here. It's 7. Oh, yeah, we do. Yeah, this is the one where. Yeah. Right. There you go.
Oh,
So this is what you get when you put the hexagon in there. 1, 2, 3, 4, 5, 6 makes up the original hexagon. 0 is the suspension vertex. And when you extend this one, you get an infinite plane.
Yeah.
Which of course is why hexagons are the best shape. Triangles are good, they're just hexagons, but in disguise.
Where did we get to with the 5? The path of length 5, or path with 5 vertices and 4 edges. Did that?
We did. Okay. Is that it? Is that still ahead? Okay. Very good. Okay, so nice. That's a good one. Hey, is that the best looking one we've had?
Yeah, what I'm noticing is that none of them seem to be extending off 2. I think, I suspect this one doesn't extend because it can't extend off 2.
Right.
So what's happening is it trying to extend off all vertices, and then if it can't go from a certain direction, it doesn't anymore, and then it's got to keep searching. Is that how it's operating?
Yeah, that's probably how it's operating.
So if it tries extending off 2 and can't do anything, it just keeps going off the other.
Yeah, so it tries extending off 2, but if it can still extend off of vertices, then it will just keep on going.
Yeah. Oh, sorry, no, 3. 3. I suspect you. So it's extending off 4 and 5.
Well, it could also be in this case just because we're only looking at the first 10 and there are 700 outputs.
Right, yes. I'm wondering if we can extend off 1 and 2 and off 3, 4 and 5, but not off 3.
That's
Oh,
true.
Right, extend off 3. So, there should be a path of 3. What's the path of 3?
Maybe that one hasn't extended off 3, just used it. Oh yeah, it looks like it just used 3 to extend 8.
So it's inconclusive. It's not telling us yet whether we can do this one.
Yeah, it'd be nice if there was like a theorem that's like if you can't do it within 5 steps, that's it, you can't do it at all.
Yeah. Well, there might be some theorems like that, although it won't be the same number for all input graphs.
Alright. Are there any other graphs you want to run it on?
like 3 dots, maybe?
Oh yeah. That might be a bit too much. 6 steps. Six steps.
So this one, we know there are infinite extensions and also finite ones. Can we?
Yeah, so there's a cube, there's like the tree. I think I was thinking of like you have squares within squares with the corners connecting to each other.
Yeah. Okay, so it doesn't build any final one. Right, so dots. Well, that looks pretty nice.
Yeah.
Trying to go some cute.
Go from one. So it looks like we have a hexagon, and then coming off each vertex, we have go to another vertex, and we can perhaps join up to another hexagon. So we've got hexagons joined together at vertices.
Yeah.
Would make a
Does it have to be a hexagon?
Not really
no.
tree line.
Yeah, it can be anything tree-like. It could be pentagons joined at vertices, or squares joined at vertices.
Tree line.
Yeah, it can be a tree. It can be infinite, or it can be another branching one. It could be just some polygon joined at vertices.
Does it output like a cube?
It didn't output a cube in this case. Though the cube, it can be a cube.
It can be a cube, yeah.
Yeah. So maybe it might have gotten close to a cube.
It's a tree. Tree. Another tree. Another tree. We haven't got a cube.
Yeah, but a cube. Well, we could try running it for 6 steps. Bold.
The cube has 8 vertices. We start with 4.
Yeah.
You can only add 4 vertices.
Oh,
So more steps won't help.
that is the program then.
Right.
I don't like to hear that. No. That kind of looks like it could be a cube.
Except it has 9 vertices.
What if you look at vertex 9? Or get rid of vertex 6, connect 9 to 1, 5 to 2, and 4, 1. You would have ended up with a cube, right?
So, but it's not finding a cube.
Yeah.
That suggests it's not looking at all possible cases.
Yeah. Which is unfortunate.
Yeah.
Suppose we have to leave a note for future us.
Yes, it's not exhausting all possibilities.
I think I might have been working on this problem before. Yeah, so, well, I think we're not actually looking at, we're not looking at every possibility for connecting it. So what's quite a while ago, so.
Yeah. Yeah, it's several months since we looked at this. So remembering exactly what we were up to is
Well, that's a good note for the future.
Yeah.
Any double graphs you wanted to run on?
Windows is important for the system.
No, I don't know if any of the graphs there or what.
Oh, that's all right. George, do you have any graphs you wanted to?
well, no, I think it would be good to start looking at some bigger graphs, but we want to.
Oh yeah, sure, yeah.
We want to be sure that
It actually works.
that we've got it working properly, and that it's going to work reasonably efficiently.
Yeah, if it doesn't, as long as it doesn't take too long or something like that.
Yeah.
Yeah.
So how many graphs were there with 11 vertices? It was a huge number, wasn't it?
Yeah.
So once you start seeing graphs with many more vertices than what we've done, there start to be huge numbers of them.
Yeah, well, less than
Oh.
you have over just over 1 billion to check.
Yeah. And each of those takes Who knows how long?
Yeah.
We could be here for quite a while waiting to check them all. So we want to be a bit smarter and a bit more systematic before going to graphs that are much bigger than what we have.
Exactly. I'm sure the people in the year 3000 will really enjoy knowing the results of all 1 billion 11 vertex graphs.
Yeah.
Is there, let's go down, is there like anything other than subfocal?
Sorry, what was that?
Just wondering.
I want to scroll down on the screen.
Yeah.
I'm going to send them the link to this website.
Right.
More.
No, I thought a bit less bad about our naming convention. We just have perfect graphs. What is that even mean? It says with these, but still.
Every odd cycle of length at least 5 has a chord.
It's so specific.
Yeah.
Micro-Hamiltonian.
Cool.
Highly irregular.
Yeah.
Thinking of a highly irregular graph.
Yeah, well, maybe we can conjecture that if we start with a highly irregular graph, we don't get get an extension.
Wow. Let's try. Let's visualize it first. That's a highly irregular graph.
Oh.
It works. That's the end of that conjecture.
Yes, we know we can do that one. What was highly irregular?
Every neighbor has a distinct degree.
Oh, right.
Yeah.
Vertexes.
So, the neighbor of this one has degree 2, and this one has yeah.
Yeah.
Highly irregular. What is this strange graph we have on the screen?
Oh well.
It's strong.
Oh, there's no highly irregular one with 5 vertices.
Only 10 has a strongly regular page. 10. This looks like it came out of the 90s.
Last stroke. E Spence, is it?
It's just Ted.
Like Edward is Ted. So it could be E Spence.
You never know who Ted is. His email is just Ted.
Well, his name's Spence.
Yeah.
You win, Spence. Pretty easy. Very spectral graphs. You got Spence.
That's Ted. Oh. Yeah, Ted says his name in the title bar as well.
Right, yes.
Okay.
The last paper was 2009, so. Well, you think the page came from the 90s, would you? Or?
Yeah, that looks like a 90s page. Everything like boxed in the center, monochromatic almost.
No, I'm not such a connoisseur of web pages. I don't. What about this one? Where's this one from?
The first year of engineering corpus. Okay, this one you don't really know because this one, like they didn't put any styling on it.
Mm-hmm.
It's like they just wanted, here's the information.
Yeah.
Off you go.
Okay, well that might be all for now. Is there anything more to
No,
at the moment?
that's all I've got to show.
That was a lot. Don't worry about it.
Sorry?
Yeah, that was a lot to look at. Yeah.
You got a lot to look at?
Yeah. I
Yeah.
really enjoyed it.
All right. Well, okay, well maybe we're going to do something else now. So what would you do? Just look at some more of these examples and maybe look up some of the Escher pictures and the maybe Ted's web page and that sort of thing.
It's a web page. I'm sorry, Ted. It's just such a nice page.
Making me self-conscious about the slides I'm writing now. You probably tell me that they're.
I'm sure they look fine.
Oh yeah, you want to go through your slides or something?
Well, I could. I'll probably better keep working on them. I can.
I haven't seen the slides there.
You want to see this one? Let's see if I can join Zoom.
Okay, they look fine. I mean, yeah, they are just using the same template everyone else uses.
Well, I can try different colors. You see.
That's what I'm
Um, oh, no, I'm not going to do that. I can put much more easy. Oh.
Recording in progress.
Where's it
Okay.
Oh, it's okay.
Yeah. Thumbs up. What?
Oh.
Oh, that's really strange. Just going to make that size of me. No, it's the size.
Okay. That all makes sense.
That's so sad. Oh, you got your computer.
Did you stop recording?
Is it recording as well?
Or it's recording, yeah. Yeah. Alright.
Okay. So these are the slides.
I think I can't make any judgment on these because it's the same template that I used in one of my courses.
Hi, so you've done the same
Yeah.
same style. Okay, so this is using
Beamer, right?
Beamer, yeah. And you can pause some of the slides, so you see I can show things bit by bit.
Mm.
I can put in all of these pauses, yeah.
Fancy looking H.
Sorry?
Why do you use the fancy looking H?
The H is used to distinguish it from one type of group from another. So there's a group G, but then there's a group H of automorphisms of G. So I'm using different types of letter to indicate different levels of
Right.
things I'm looking at. And then the Z here is the integers. Different font for that. So I have to put in, I'll put in some pauses here. Oh, why is that? Oh, I should fix that. So this is talking about isometries or automorphisms of trees, infinite trees. Right, then there's the references, and then there's they go over the page. So I'll have to put in a page break to.
Okay, references to the leading behemoth.
Yeah. Some. Go back. So I can set some of the colors. You can use different styles.
You're still sharing just the slides.
Yeah.
Um,
That's just intended.
so,
Are you still in a meeting?
Yeah, we are.
oh, why is it not?
It says slides for like 2 days.
Stop sharing.
Different application share. Okay. Yeah.
Yeah, you can change your color scheme. You like that better?
No, that is no.
Nah, I think
that's
it's a
not
bit
it.
too bright.
Yeah, that's not
It's a
it.
bit
She
too
is
bright.
You like that one?
It's like you guys are like designed
Green text.
the green just
You
doesn't.
made that bad on purpose.
That was just some random colors. Let's try a different theme.
Oh, this is the important math that we're doing now.
Yeah, you can waste a lot of time doing this.
And feel like you're actually doing work.
Yeah. Let's try one more.
Ooh.
Oh,
Interesting. It is
That's
much
not
stronger yellow, but
it's not that bad.
yeah, it's not that bad. But I feel like just the choice of yellow is going in the wrong direction. But like,
What's going in the wrong direction?
yellow.
He thinks yellow is not the right way to go, but
it's
does it look? It looks pretty good.
yeah, it's infinitely better than the green yellow.
And the green one. No, that's not very high praise.
Yeah, so I believe it's because when you like, for example, the definitions in remarks, right? The darker tone of yellow just doesn't work well, in my opinion.
Sorry, what was that again?
like as seen in the definitions and remarks, like the darker tone of yellow is just not as appealing to look at as other darker colors. Like,
Oh, right. Yeah. Okay.
yeah,
I think
but
that's what we
yeah, but the yellow no top is fine. I have no issues with it. It's just that yellow does not have yellow is only equipped for a wider.
Yeah.
Is it tone or is I think it's tone, the visual arts term.
I don't know what it is.
Again, this is
Same.
that takes the ruler just
Oh, blue. All right. Well, that's the fun for me to have once I've finished actually writing the slides.
Oh,
All right. Why don't we finish up there, and I'll get back to playing with the colours of the slides.
yeah, okay.
Well, thank you, Marcus.
Yeah, thank you, Marcus.
Thank you, Marcus.
Yeah, we'll have to get back to this program and see if we can get make some more progress.
Yeah. Thanks. See you later.
See you.
See ya.
Okay, well, why don't we finish there for today? Should we meet again tomorrow?
Do you have anything you want to do for tomorrow?
Well, we can keep looking at these questions. By the way, it's not got my shirt here. There's a solution to
Oh,
the questions there, right? So we've got
oh,
what's that? 6 dots.
yeah, 6 months. Oh no.
Yeah, why don't you keep thinking about some of these? The line of 5. I don't think we ever resolved that one, did we? See if you can think about that one.
Oh, your battery is running low.
Right, this one.
See, this is trivial one. Oh, side. Which side? Other
Yes, so
side.
these have matrices that have zeros on the diagonal.
Yeah.
And then ones above.
Okay.
And ones below.
Sometimes I lose sound when I do.
And then 0 everywhere else. So why don't you see if you can make some progress with that one in the next by tomorrow.
Sure.
And should we meet again at 10 tomorrow?
Yeah, okay. Yeah.
Yeah, that's good for me. All right then. So I'll get back to my slides and I'll give my seminar tonight. And I'll see you tomorrow.
Yeah, have fun.
Yeah.
All right, see you.
See you. And we
Stop doing.